Hi, everybody. Um, we've been talking about transistors, and today I want to continue our discussion and focus on, well, how transistors have taken over the world. Basically, you'll see that the properties of transistors improve as you make them smaller and smaller and smaller, okay? And so that's what people have done. And we'll learn a little bit about how that works. And finally, we'll talk about what the limits are to scaling. How small can they be? Okay, so here, let's take a look at an outline and then we'll get started. All right. So last time, we talked about the physical principles behind transistors. And we introduced the field effect transistor, which is perhaps the dominant type now, and the bipolar junction transistor, which is related somehow to the properties of diodes. Okay? But today what I'd like to do, Today what I'd like to do is to talk about, well, we'll call it Moore's law, how the transistor has taken over the world. I want to start with a really brief history so you can see where these things came from. And then we'll talk about scaling laws, how the properties of transistors change as you change their size. And what we'll find, I think we found this in an in-class problem last time, is that they generally get better and better, okay? We'll learn just a little bit about how tiny transistors can be made using photolithography. Okay? And that'll lead us to one of the most famous examples of exponential growth around, what's called Moore's law. And finally, we'll consider some limits to scaling. What limits how small transistors can be made? Well, that's what we'll look at. So hang on, and we'll just go and get started. Okay, very good. So here's a very, very brief history of the transistor, just to give you an idea of where things came from. The principle of the field effect transistor was proposed way back in 1925 by Julius Lilienfeld. Proposed the idea, but no devices were made at this time because they didn't have enough control over the kind of materials that one would need to make a transistor out of. The first working transistor was a point contact transistor made in 1947 by Shockley, Bardeen, and Brattain, who are all pictured here. They all worked at Bell Laboratories, and of course, this is a very famous discovery. But the point contact transistor itself was not a very useful device. It demonstrated the principle, but it was very delicate and expensive to make. In 1948, the first practical transistors, bipolar junction transistors, were made by Shockley in collaboration with these others. In fact, there are a lot of interesting stories about this, but one was that Shockley really wanted to start by trying to make a field effect transistor. This was the most simple, most elegant design that people had thought of. But it turned out there are a lot of problems with trying to make field effect transistors. One has to have very good control over the surface of the semiconductor, where there are normally lots of defect states that, as it turns out, would prevent these things from working. And the bipolar junction transistor was really developed by Bardeen and Brattain, while they were messing around trying to make the other type. And because they made some progress here, they decided to push forward on that. And Shockley was very, very unhappy about this, but eventually he came around. On the other hand, the MOSFET, the device that we talked about last time, field effect transistor, was developed in 1953 by Muhammad Atalia, pictured here, and Dewan Kang, pictured here. Something all these people had in common, okay, they were all men, that's true, but also they all worked at AT&T Bell Laboratories. So it used to be that the telephone company, AT&T, had one of the most important technological laboratories in the country, Bell Labs in New Jersey. Okay, those days are gone, but it's kind of interesting. MOS transistors are very well suited to being miniaturized, as we'll talk about next. The first integrated circuits, multiple transistors on one chip, were made in 1964. And the first microprocessors, so computers on a chip, were made in 1969. Okay. Something else, the early transistors were all made in germanium. Okay, germanium, of course, is a semiconductor. In some ways, it's easier to work with than silicon, and some of its properties make it more amenable to making transistors. But in general, silicon is much higher performance. And once people had mastered the technology of making transistors out of silicon, this completely replaced germanium, except for a few special cases. Okay? And silicon, in the end, is a much cheaper material, which is good too. Here, hang on one second. Here, let's talk about scaling laws for transistors. Okay? Why smaller is better. So as we go through this discussion, I want to think of a kind of prototypical field effect transistor, okay, that has some dimensions, length and width. This is the gate that I'm drawing here. And then we might imagine the source and drain contacts being right next to it, like so. Oops. Okay, so we have source, drain, and gate, and then we have dimensions, length and width. All right? So let's see what we can figure out. The first thing is the most obvious. The first concerns the relationship between the size of the transistor and the number of transistors you can fit on a chip. Okay? Well, I guess that's pretty, it's so easy we don't even need to think about it, but let's think about it anyway. And we'll do this just as an example of a scaling law. So the number of transistors that can fit on a chip, this number is clearly inversely proportional to the size of each transistor. The smaller they are, the smaller the area they occupy, the more you can fit on a chip. And so this is proportional to 1 divided by L times W. So obviously, the smaller you can make the transistors, the more you can fit on a chip. And that's important for a couple of reasons. One is to make small devices, but the other is that what you're paying for is the semiconductor. You're paying for the chip. So what we've just learned here is that the cost, as you make transistors smaller, the cost per transistor should go down. So smaller is equal to cheaper. Okay? Nothing mysterious about that. I just wanted to illustrate how this works. Here's something a little more interesting. How about the switching time? How long does it take to switch a transistor from on to off? Well, in order to do this, we have to inject or remove a certain amount of charge from the channel. And this, this process, this time, is governed by an RC charging time. It's governed by the resistance of the channel times the capacitance of the gate channel capacitor, okay? Because the capacitance determines how much charge we have to inject, and the resistance determines how fast we can get the charge in there. So it's governed by this RC charging time. The resistance of the channel, it's easy to work out, is equal to the, it's equal to the length divided by the cross-sectional area, that's W times the thickness, T, and divided by the conductivity of the material, okay? On the other hand, the capacitance we found last time, the capacitance can be written, it's the area of the gate, which is L times W, divided by the distance between the gate and the channel, and times the dielectric ratio and permittivity of the vacuum, okay? So the tau, RC, should be L over W times T times sigma times the capacitance, which is L times W over D epsilon R epsilon naught. And you'll notice that this is proportional to L squared. So the switching time is proportional to L squared. Of course, to make a fast computer, we want to make the switching time as small as possible. And the smaller we can make the transistor, the faster we expect to be able to switch it from on to off. So that means that smaller is also faster. Okay? Not so bad. Here's one more. How much energy does it take to switch a transistor from off to on? Okay? Well, the energy is equal to the energy that's stored in the capacitor when it's charged, because all that energy is dissipated when it's discharged. Okay? And of course, the energy stored in a capacitor is given by 1/2 C V squared. So this is 1/2 times the capacitance of the gate channel capacitor times the voltage threshold squared. We've already seen last time that the voltage threshold is independent of size, independent of gate area, so that the switching energy is just proportional to the capacitance. And so it's just proportional to L times W. So small transistors take less energy to switch. So smaller also equals lower power. Okay? So not so bad. We figured out a scaling law for transistors. We figured out that smaller transistors are cheaper. Smaller transistors are faster, and smaller transistors consume less power per transistor. So hard to go wrong with that. So it's pretty clear we'd like to, if we want to make progress, we'd like to make the transistor smaller and smaller and smaller.